Robotics by Joon. Hi, my name is Joon. I'm going to introduce a series of videos by which you're going to learn about the basics of robotics. You will learn how you can mathematical model your real robots into equations, how you can make controls for them, how you can make trajectories for your robot. And we're gonna do it in the Python language. So we will start from the basics and we will try to take it to advanced level. We're gonna use the ROS. ROS is Robot Operating System. I will recommend you to install the ROS on your Linux system like Ubuntu. So without wasting any time, let's start. In this specific video, you're gonna learn about the kinematics, how you can write your kinematics equation in Python language, how you can make trajectories, and we will see the simulation in Turtlesim. In this video, we will going to use Turtlesim because it's beginner friendly. Later on, we will going to make our own robots in the gazebo environment and we're gonna control. So this is the overview. We will see what are differential drive robots, what are unicycle like robot, how we can write the kinematic model, how we can write the trajectories, and the Turtlesim simulation in Turtlesim. For the trajectories, we will learn how the robot will going to make a circle, how our robot will going to make a 8 shape trajectory. Okay, what are differential drive robots? A mobile robot with two independent driven wheels on a common axis and a third passive caster wheel for stability. I think you have already seen the cleaning robots. These are getting very much famous nowadays. These robots generally have three wheels: the left wheel, right wheel, and a caster wheel. So the left wheel and the right wheel are directly attached to the motor, and the caster wheel is just for the stability. Like in this figure, you can see directly. It's not covered, it doesn't have a body, so you can see it. So the left wheel and the right wheel are directly attached with the motors, and there is a one free caster wheel. So the caster wheel have the property it can rotate anywhere, like the wheels on your chair, moving chair. It can rotate anywhere. Okay. Now, if you want that your robot should move in a forward direction, then you just have to give the rotating speed, maybe a clockwise rotating speed to both the wheels, left wheel and the right wheel, with the same speed. Then you're gonna see your robot will going to start moving forward. And what about moving the backward? So you just have to rotate them into anti-clockwise direction with the same speed. What about making turns? How your robot can rotate? In that scenario, either you should give the opposite velocities to the left wheel and the right wheel, or you can rotate one wheel faster than the another wheel. As a result, you will see your robot will going to start making a curve. That's how you can control these robots. Okay, what are unicycle like robot? A unicycle like robot is a type of mobile robot whose motion is mathematical model after a unicycle. So just think of one wheel on a ground. For that, you just have to give uh, two controls: the linear velocity and the angular velocity. So if your robot is here, let's say a point A, and if you want it should reach at point B in a straight direction, so in this scenario you just have to give the linear velocity. By giving the linear velocity to the robot, both the wheels, left wheel and the right wheel, will going to rotate at the same speed in the forward direction. But it depends on the magnitude and what is the direction, whether it's a positive or the negative. If it is a positive, your robot will going to move in forward. If it is a negative linear velocity, your robot will going to start moving backward. And if you want to make a turn, just give the linear velocity and the angular velocity, you will see your robot will going to start making a turn. There are few assumptions. The first assumption is that your robot is moving in a 2D surface. So it's not a surface like a mountain. No, it's a 2D plane smooth surface. And the second assumption, it cannot move sideways direction. So like if you have a car and if you want to do a parallel parking, then in that scenario you have to move your car forward, then move your steering and comes backward. That's how you can do a parallel parking. Okay. uh, Now what is pose? You can describe the pose of a robot as the information, as a three information: the x, y, and the theta. In a simpler term, like just think about your room and where your robot is placed. So this how you can represent the pose. X and y are the position, robot position in the x-axis and the y-axis. Just think of your corner of your one of the room and take it as a origin. Then you will know the x and the y coordinate of your robot, and the theta is the orientation of the. For example, this is a robot, it's looking towards through the camera, so it's at the 0 degree, and now it's like at a 45 degree maybe, and it's like a 90 degree. So this is the heading. So x, y, and the theta is called the pose of a robot. And these three, don't be afraid, it's just simple equation. X dot is the derivative of x with respect to time, and v is the linear velocity, and theta is the angle of the robot. For this, y dot is the derivative of y is equal to the linear velocity sine theta, and theta dot is equal to the angular velocity. So how these equations are useful? So just think, you are giving linear velocity v equals to 1, maybe 1 meter per second, and you will not give the angular velocity at that time, so your robot will going to just move in a straight direction. Theta is 0, so if you gonna integrate these equation with respect to time for 1 second, then you will see x will going to come 1. So your robot starting from 0 0 will going to reach at 1 comma 0. So because your sine theta is 0, so it will going to 0, and you are not giving the any angular speed, so theta will be 0. So that's how these equations are very much important. Okay, let's code. Okay, let's start coding. I have already put the codes. These are not the packages, these are just the ROS node which I have prepared and put it on my GitHub, so you can just directly download and put it inside your packages. So let's open the terminal here, and let's first source it. Here we're gonna source. Okay, now we're gonna create our own directory. Let's name it to robot.ws. Okay, and we have created. We can go and check. Here is the new directory which is created, and it just have only src folder. Now we will go inside this robot.ws. Let's check. Okay, now we will do colcon build, and let's check. Now we have extra folders: the log, install, build. these folders are not created by us, it's automatically compiled by the Qualcomm build, and you will create your packages inside src. So cd src, so you should create package here. Now there is nothing inside it, we're gonna create our own package. What could be the name of the package? Let's make it maybe just robot pkg, robot package. Okay, so I would like to tell you about the command. So we will type ROS2 package space create is dash build type, and we are telling that it should be Python, and we are already giving the license type, and here the robot underscore package is the package name. Okay, so the package is created. Now you can see a package is created with the name robot package. Welcome src, and here you will find our package. So our code should be inside this robot package. In this package you will see this folder robot package, and here we have to put all our codes for the node. So here we're gonna put our Python files. You can download these 3 files, 1, 2 and 3. I have already downloaded it, and here in the downloads. Okay, and I am going to paste it directly there. So this is the directory which we have created in src. Here is the package name robot package, again robot package, and you're gonna paste your files here. Now you have to edit .xml plus setup.py. So let's first edit this. Open with, I like Visual Studio, so I will open in this. Okay, here just after the license you have to add here 2 lines. I am going to add those lines. These are the 2 lines which you should add. These are adding these libraries. This is for the ROS and the Python, and this is for the standard messages. And remember to save it. Okay, so this is done. Now we will modify setup.py. I will again open it with the Visual Studio, because as it's my favorite, and we're gonna create the entry point here. So first maybe let's call it kinematic. Okay, and then equals to your package name. So what's the package name? Our package name is robot pkg. I will just copy from here. Okay, dot your ROS node name, and then main. What is the ROS node name? This is the ROS node name. Here we're gonna see, open this kinematics.py. So here you can directly write kinematics. You don't have to write .py. Okay, now we can write for the circle and for this all together here. Just copy this, paste. So take C and maybe I will write like 8. Okay, here kinematics circle underscore turtle, turtle sim. Okay, and at the down it's kinematics underscore 8 shape underscore turtle sim, and that's all. So we have all these three here, and we're gonna call it like kin underscore c and kin underscore 8. So we're gonna save it also. Okay, and open the terminal and do colcon build. For doing the colcon build, you should always come here. Okay, it's done. So now we can call this package and let's check if it works or not. So ROS2 run, and the package name is robot package, and what is our ROS node name? It's kin. So let's see. ROS node package not found. Okay, so we have to source it. Let's source it. So we have just sourced it, and now let's try. Okay, it has started. So now I will open the code and I will going to tell you what I have did in my ROS node. Now we will try to understand this code. Here we are importing the libraries. Here we have declared the variables, the x, y, and the theta. So this is the pose of the robot. So we are assuming that the robot is at origin, at the starting. Here are the kinematic equation. Maybe I can show you from my slide here. So these equations are written here. So x dot, here we are directly multiplying with the dt, so we are integrating it. So our new x is the old position of x plus the linear velocity into math of cos theta. So it's like we cannot directly write the cos theta here. We have to import the library, import math, and then we are saying math dot cos theta into dt. So that's how I have written for the y and for the theta also. So after that, I have created a for loop here, and I am asking the user for the initial linear velocity and for the angular velocity, and after that I am sending those values in this function. So let's open the terminal and check it. Okay, let's put 1 and 0. So our robot should move in forward direction. So as you can see, the robot have moved to in the forward direction. X equals to 0.1 and the y is 0, theta is 0. So now let's create one more time the same. Now the robot have moved 0.2. Now let's move backward in the backward direction, but with the higher speed. We can write -2 and the angular velocity may be 0, and now you can see it have already reached the origin. So that's how these kinematic equations are very much important, and maybe you can just write 0 0 just to finish it. Okay, so it's finished because I have already the for loop. here ROS to run the package name, remember, and here you're gonna write the ROS node name. Okay, let's move further. Okay, let's have a look. What is trajectory? A trajectory describes the time evolution of the robot pole, which includes like where the robot should go and when it should be at each point. So there is a difference between the path and the trajectory. Here the path is just x and y, but the trajectory is x, y, and the theta at a specific time. So we can define the path as the geometric curve in space, but the trajectory is the path plus the time. Okay, the example for the path, a circle drawn on a paper, is just a path, and the trajectory, a robot moving around that circle at a constant speed. So why it matters? It ensures the smooth robot motion, the first point. The second, it enables the precise navigation and the control. And the third one, it is critical in motion planning, path following, and autonomous navigation. Okay, let's move forward. We will learn how we can make a circle. So just to make a circle, the v and the omega should be constant, and how we can calculate it. So first we have to assume the radius of the circle, and we have to tell the linear speed for the robot. So by assuming these two parameters, we will calculate the angular speed. And when you're gonna put this linear speed and the angular speed onto the robot will start making a circle. It's simple. So the robot will move in a constant linear velocity, and to stay on the circle, its angular velocity omega is fixed, and heading the theta continuously changes to stay at the tangent to the circle. Okay, how you can imagine this? Imagine holding the steering of a car at a fixed angle, and the car keeps moving in a perfect circle. So that's how you can think. There is a second type of trajectory. It's like a 8 shape. So its equation is complex, but nothing to worry, I would say. The x is defined as this is y, the a is the scaling factor, and the phi is the phase offset. The x dot and the y0, or you can say x0 and y0, are the center offsets here, and the phi is equals to k into t. K is the speed parameter controlling how fast the path is transferred, and t is the time. Okay, now you have to do the first derivative of these equation here, and also the second derivative. And this is the v. V is the linear velocity which you going to publish to the robot, and this is the formula for the omega. Okay, let's go. Okay, these are the Python files which we have already put in our package. Let's analyze it one by one. This is with a circle. Here we are importing all the libraries which are needed, and this is the publisher and the subscriber. So we are publishing our linear velocity and the angular velocity at this ROS topic, and here that's how we are subscribing to the turtle pose. So we are taking x, y, and theta, and we are saving it into the list. We have created the empty list, and whenever the data is coming here, we are saving into the Python list. And here this is the radius which we have assumed. Here is the linear velocity for the robot, and this is the angular velocity calculated as I have shown you the formula in my slide. Okay, and let's move forward. Here we are publishing the linear velocity and the angular velocity. This is for the kinematics. Okay, let's move down. Here this is the code for plotting. And now we will see the 8 shape. The same, we are importing, we are publishing, we are subscribing by this, and we have created the parameters and the variables here. And this is for the offset for centering. Okay, and here these are the position. These are the equations which tells you the first derivative, and these are the equation for the second derivative with respect to time. And this is the formula for the v, by which we are calculating how much linear velocity we gonna send to the robot. And for the, this is for the omega, angular velocity. So if you want to watch the equations, you can just watch my slides and you will get these the same equations. So these are the two functions, the kinematics, and again this is the code for plotting and saving the image. Let's directly jump into our terminal, and for the circular it was C. Let's open the turtle boat. I think to open the turtle boat it was, yeah, ROS to run Turtlesim and Turtlesim node. Turtlesim is the package and Turtlesim node is the node name. Okay, so now we want that our robot should make a circle. So this is the simulation, and in this the robot is making a circle. So you could see. Now we have to press Ctrl C to stop this ROS node. Okay, and the plots are already saved, so we can go in our directory back, and here you will see the plot. Okay, so this is the desired circle which we wanted to make, and this is the actual path the robot have traveled. So there is no controller, so it's a open loop. So that's why there is a difference. In the future we're gonna make some controllers and it's gonna have a closed loop, then our robot will going to make a precise circle. Okay, now let's move ahead to our second node, which was with the 8, if I remember. Let me check the name. I will go in the setup, and okay, yeah, it's correct. Now it have to make a 8 shape. So here we got our robot, and we gonna see if it makes a 8 shape or not. Okay, it have started from here, and now it's making a 8 shape trajectory. Okay, so it works. Yeah, so thank you so much.